All right. So we will leave that to a little bit later. The third term is the error generated from this very time step. All stability or the accuracy of any particular scheme is going to be a compound of these three terms. Okay, so zero stability, the first term we already analyzed. Eigenvalue stability we'll analyze later, and the last term comes from accuracy analysis, right? It is something we did last week. And also the last term is going to have an order that is one more than whatever accuracy analysis we derived in approximating the derivative. But that does not mean an ODE solver is more accurate than a derivative approximation scheme, because the smaller the delta t is, the more frequent or the more times this error term gets applied per unit time. Right? Yes?
Just to clarify, so this is the global error?
This is the global error, yes. This is the evolution of the global error from one time step to a next time step.
Is the global error always one order above the local?
No. That's what I was saying. So let me actually give one more page, dictate one more page to that, dedicate one more page to that. Let me just delete all the stuff in here. Okay. Again, let me write down. So my error at n plus 1, okay, is equal to that's for forward order only, e at step n plus my df du times en times delta t plus o delta t squared, right? So that's for one step. If you accumulate that over many steps, so what we'll have is that e of n plus 1 is going to be okay, so if you combine these two terms into a matrix, so basically identity plus delta t times df du, right? So we call this matrix our matrix B, for example, times en plus o delta t square. So what we have is we have B times en plus some small error. Okay, then we have en itself is from B times en minus 1 plus o delta t square, right? Then another plus delta t square, right? And then you can expand more and more. So what you can see is that when we get to the very end, we have a b to the nth plus 1th power times e0, the first term, and then we'll have many terms. Each one is going to be o delta t square, right? O delta t square plus, and the number of terms is proportional to n. So, right? Okay, so this is basically why the error accumulates. And the smaller delta t is, the bigger n is at a particular time, right? Which is saying that this is proportional to 1 over delta t. How many terms you have in this accumulation is going to be more as you have more delta t. So if you combine them, you get back to O delta t. That is assuming this B does not amplify your error, right? Yes? There is no one order difference. So in getting from my local error to this equation, I already multiplied both sides. So this is the local error of my forward order scheme. From here to this error equation, I have to multiply both sides by delta t. So in the update formula, I have one more order of accuracy. But then I have to apply that higher order of accuracy for many times. That cancels this additional order of accuracy. So that's why the global and local error, it becomes the same again, right? So from here to here, I add one more power. And then because of the accumulation, I decrease one more power. So they cancel out. Local and global order of accuracy became the same. All right. did that you still look confused?
Yeah, I understand the logic. I'm just saying, if I want to calculate it on my own, I'm gonna try to see the lower order of accuracy of the method. I would normally end up with this equation that has the second order, and I would assume that it's one more order than the local accuracy. But yeah.
Yes, whenever you derive this formula, you are supposed to get one more order of accuracy than either local or global order of accuracy, right? And the reason is, from the local order of accuracy analysis, you multiply both sides by delta t. And then to get from this point to the global order of accuracy, you need to repeat this formula for 1 over delta t many times, right? So at the end, local and global order of accuracy are the same, assuming your system is stable. So that is actually a theorem officially proved as the Dahlquist equivalence theorem. That's saying the prerequisite is the local order is greater than 0, which means you have at least a first order scheme, right? Plus 0 stability. If you have these two things, 0 stability means no eigenvalue is outside the unit circle. So here this 0 stability means that it's okay to have eigenvalues exactly on the circle, but no eigenvalue is outside the circle. So if these are true, that gives you the global order is going to be equal to whatever local order you have. So that's a result that can be mathematically proven, right? Basically, we almost proved it. You just to be a little bit more careful on some of the linear algebra we did. All right. So basically, you can that's very nice because it enables you to guarantee a good ODE solver as long as you can do Taylor series analysis and eigenvalue analysis, right? If you know these two mathematical tools, you can now guarantee that an ODE solver is good.